Yeah, so I've been on sabbatical at JPL working with some folks there, Felix Lander and Tony Lee, so this is through some of the work that we've been doing, but they haven't seen the slides, so if there are any errors, it's all my fault. So I'm going to be talking about the wind-driven variability of the AMOC at 26 North, focusing on using the rapid moorings at 26 North, and I'll talk a little bit about what those are, and then GRACE satellite measurements, and I'll describe that a little bit as well. So I study the overturning circulation, which you may know of as the Great Ocean Conveyor, although you probably do know it as the overturning circulation here. And the overturning circulation refers to the northward flow of warm water in sort of the top 1,000 meters with the southward return flow at depth. And the latitude that I'm particularly interested in is 26 North in the Atlantic, so right around here. And there are many reasons, and you probably know many of them, for why we're interested in the overturning circulation. But just to give you a little bit of background, the overturning circulation in the Atlantic carries about 25% of the Earth's poleward heat transport, and it has a maximum northward heat transport around this latitude in the Atlantic. So this is showing estimates of heat transport with against latitude here. And so 26 North is around here, and you have a peak in the northward heat transport. And so this northward heat transport is one of those things that keeps the temperate high latitudes, particularly, say, in the UK, where I'm now living, a more congenial temperature than, say, if the overturning circulation weren't there, although not nearly as nice as here. I think they had snow a couple of days ago. And so some of the interest in the MOC has been that climate simulations suggest that a large input of fresh water may slow down or even stop the overturning circulation. And what happens if you stop this circulation is that you change the regional distribution of temperature quite a lot. And so this is a map showing in one of those simulations what would happen to the temperatures if you shut down the MOC. And so you see, well, in the UK, for instance, it gets a lot colder. So there's a lot of interest in this because of what would happen if it slows down, and also because the IPCC model suggests that over the next 100 years it will slow down. So just a little bit of additional background. This idea of what the overturning circulation is here, given by the conveyor belt, suggests that you have these sort of ribbons or narrow confined currents of water that are carrying water northward. So you have the Gulf Stream here and the North Atlantic Current, and then you have this return flow that's confined in the deep western boundary current. But actually this return flow is not really, and even the northward flow is not really necessarily confined to one location like a river. And so there's this idea that you have interior pathways that are important as well. So these interior pathways, this is showing CFC spread in the water column, showing that the region of, and high CFCs means recently ventilated water, so the region where this recently ventilated water spreads to is not confined to the deep western boundary current, although certainly at 26 North there's a little higher concentration there, but it's actually spread across the North Atlantic. So this idea of interior pathways also becomes important when you want to talk about the overturning circulation. So how does this play out in the observations that we make? I'm going to tell you a little bit about these observations. This project is called RAPID in the UK, and part of it in the UK is funded by the Natural Environment Research Council. It's called MOCA in the US, funded by National Science Foundation, and the Western Boundary Time Series program is funded by NOAA here. So it's this large joint program. It's been running since 2004, or in the water since 2004. And I'm going to, just for short, refer to it as RAPID 26 North. The observations that are involved are, we want to know this northward flow of water in the top 1,000 meters and the southward flow of water at depth. So that northward flow of water in the top 1,000 meters includes the Florida Current. So that's one of the terms, and that comes from the Florida cable measurements. It also includes northward flowing Ekman transport, so the top 100 meters or so of water that's estimated from reanalysis winds is part of that overturning circulation. And it includes the southward flowing gyre water. So these red sort of branchy out things are the southward flowing gyre water. And so we need to estimate how much water is moving in the net northward here and how much water is moving net southward below. And this is what we're calling the overturning circulation. So the main components that we're talking about here are the Florida Current, Ekman transport at the surface, this gyre or interior transport in the top 1,000 meters we're calling the UMO, or upper mid-ocean transport, and the stuff beneath we separate sort of arbitrarily, semi-arbitrarily, into two layers called the upper North Atlantic deep water and the lower North Atlantic deep water. So this is what would be traditionally considered the waters that make up the deep western boundary current. And the actual MOC, the thing that we call the MOC, is the net northward transport. So it's the Florida current plus the Ekman transport plus the upper mid-ocean transport, which has a negative sign. So this is sort of 30 sphere jumps northward, 3 sphere jumps northward, and maybe 18 sphere jumps southward. And when you add those up, you get the overturning circulation strength. And since it's an overturning circulation, it's equal and opposite to what's coming southward at depth. So the inverse, because we define the MOC as a northward transport, the inverse is basically the sum of the upper and lower North Atlantic deep waters. So when I talk about it throughout the talk, I'm going to be referring a little bit to these two different layers, or these to these different components, but the MOC is basically the sum of what's going northward in the top 1,000 meters, which is equal and opposite to what's going southward below. And these observations are made, as I said, with the Florida cable measurements and the Ekman from the winds, and then the interior transport measurements are made with moorings. So the two components of that are direct current meter measurements in the west, just off the Bahamas, within 25 kilometers of the Bahamas, and the rest is through geostrophy. So we measure density at the east and west with difference of density, and that tells us about the meridional shear. Okay. There's a little bit of a whirlwind introduction to the observations. I'm hoping some of you are already familiar with it since this institution is involved with it. But I just want to highlight a couple of key strengths of these observations. So one of them is that these measurements are really transbasin. So they go all the way from east to west. And what that means is that if you had only measured, say, halfway across, the moorings that you had in the middle would see a lot of eddy activity. And so that eddy activity would sort of artificially inflate the transport variability that you observe. Because you'd be, when an eddy is crossing one of these moorings, you'd be observing sort of the dynamic height anomaly associated with that eddy, and the transport difference between those two things would look anomalously large because you're only halfway through the eddy. It also means, for instance, when you have this interior circulation of the deep western boundary current or those deep waters, that actually if you're measuring all the way across the basin, it doesn't really matter where the water is flowing southward. You're still capturing the transport variability as long as you're at the edge of the basin. So that's one of the key strengths of the rapid observations. And the other one is that they're full depth. So by measuring from top to bottom, we can estimate geostrophic shear relative to a level of no motion or known motion. But because we have from top to bottom, there's some offset to it that normally we would apply by applying a sort of a barotropic value to it in order to ensure zero net mass transport, so that what goes north must come south. Because we have full depth measurements, we're able to do that in a time varying sense. So two key strengths of the observations at 26 North are that they're transbasin and full depth. And this does actually set it apart from some other observations in the North Atlantic. Okay, so before I get into the main bulk of what I want to talk about, which is the wind-driven variability, I just want to give you a little bit of a tour through what we've learned so far. So I've told you about the observations and why we care about it. This is what the actual time series looks like. So this is time since it went in the water in 2004, and the y-axis is transport in units of sphere depth, or millions of cubic meters per second. And what you see is this value of the overturning circulation estimated every 12 hours, but with sort of a 10-day filter applied in some sense. The value of the overturning circulation every 12 hours at 26 North. And so we've learned a number of surprising things from this time series. One of them is that the MOC is highly variable on timescales of days to years. And so when the first year of data came back, there was this huge variability from 4 sphere jumps to 34 sphere jumps over the year, which was much larger than previously anticipated because we have this concept in our mind of an overturning circulation that's sort of slowly varying. It's a climate-relevant time-scale sort of process in the ocean, and yet what we're seeing, what we saw from the first year of it, was that there's a 30 sphere jump range in 1 year of observations. So one of the things that we've learned is that it's highly variable. And then also, that it has a seasonal cycle. So this red thick line overlaid is the seasonal cycle estimated of the overturning circulation. So again, many things in the ocean have a seasonal cycle. So in retrospect, maybe it's not that surprising. But at the same latitude, the Florida current has a seasonal cycle that's not stationary, so it changes in time. Ekman transport, so the wind-driven surface circulation, doesn't really have a seasonal cycle to speak of. And so it was surprising when the observation showed that there's a seasonal range of about 6 to 7 sphere drops of this large-scale ocean overturning circulation. And then we've also learned that the MOC can reverse temporarily, which seems so contrary to this idea of northward flowing warm water at the surface, southward flowing deep water. But during a couple of events in 2009-10 and more recently in March 2013, the actual value of the MOC was negative. So the sign of the circulation had shifted. This was actually due to strong wind events associated with, in particular in 2009-10, a very strong negative NAO. But again, something that we hadn't previously anticipated. And then also, there's large interannual variability. So as the time series got longer and longer, more new things came out of it each time. And so in this sort of April 2009 to April 2010 period, the actual value of the overturning circulation was about 30% weaker than the mean value from the 5 years prior. So this was again surprising. Interannual variations can be large, and they're larger than those shown in numerical models. So this is just a histogram showing the annual mean MOC change from a CMIP5 model. And so these are the possible annual mean changes from the CMIP5 model, and this is what the rapid observation showed. So really outside the realm of possibility for a lot of these CMIP5 coupled climate models. And now, with 10 years of observations, we can start to think about longer timescales changes. So there's a recent paper published about the MOC time series that says the MOC has been in decline of about a half sphere drop per year over the past decade, which is an order of magnitude larger than that predicted by models. Although there's also been several studies that have suggested that this is not indicative of a long-term decline, but is actually part of the natural variability of the system, just on longer timescales than we'd previously observed. So a lot of things that we've learned from these observations at 26 North, and the one that I want to talk about today is the wind-driven surface circulation. So just to give you any questions so far? No? All right. That's good, because I have a few too many slides. But ask any questions, please. So just to let you see the whole data set, although I'm not particularly fond of this format because you can't really see all the fluctuations, but these are the MOC components that make up the northward transport. So this top panel shows those 3 components of the MOC that we add together to get the MOC. And then the bottom panel shows the 2 components of the deep flow below 1,000 meters. And so when you look at this, you see a bunch of fluctuations. There's that downturn that we mentioned, and then lots of other sort of high-frequency variations. But you can't see them. You can't see them very well because it looks like a lot of squiggles. But if you plot them on top of each other, what you can see is that now I've only taken 2 of those time series, the MOC and the lower North Atlantic deep water. So that's the transport layer, sort of arbitrarily between 3,000 meters and 5,000 meters deep. I've inverted one of them and plot them on top of each other. And what you see is that they look like they match pretty well. So when one of them goes high, the other one goes low since it's inverted. And so I want to just put forward that if we can understand the variability in this lower layer, the lower North Atlantic deep water transport layer, then we can understand something about the overturning circulation. So the rest of the talk, I'm going to be talking about the lower North Atlantic deep water transports pretty much only, and then trying to place them into context for what we know about the MOC at 26 North in general, and what we know about the wind variability over the Atlantic. Oh, right. That's all right. I think I already said some of these. Okay. So again, these are the deep transports. And I said earlier that they're interior pathways, but it doesn't matter really where the southward flow happens. that we're capturing it all because we're looking at the trans-basin transport. But just to distinguish between the upper and the lower North Atlantic deepwater layers, this is showing the spread of CFCs in Labrador seawater, which is, say, between 1,100 meters and maybe 2,500 or 3,000 meters. And you see that this water spreads sort of over the whole subpolar North Atlantic. And then this is the same quantity CFCs, but in the Denmark Strait overflow waters. So that corresponds a little bit more closely to this lower layer, 3,000 to 5,000 meters, and that's concentrated a little bit more at the west. So even though we're saying what we really need to measure is the trans-basin circulation, where the water is actually moving from north to south appears to be concentrated in the west. So for the lower layer, it's a little bit.
Show where the move is.
Yeah. Move is at 16 north. So they're about here, and at move they span from the Mid-Atlantic Ridge to the, I think these are the Antilles Islands. Yeah. And line W is up here around 39 north, and they really try and focus on measuring the deep western boundary current using direct measurements with current meters. All right. So, all right, let me just go back to this 1 second. So this is the MOC and the lower North Atlantic deepwater layer transports, and I've inverted one of them, and we think they look pretty good. I've also made a monthly bin so that some of the high frequency noise goes away.
So that's a correlation on monthly estimates?
That's a correlation on monthly binned estimates, yeah. Sorry, I've switched the timescales a little bit a couple times here. This is Ekman transport estimated from reanalysis winds across 26 north, plotted against, again, lower North Atlantic deepwater layer. So you look at this one and you say, well, actually, those look like they agree pretty well, too. I have done one thing to this one. This has been detrended. So I've detrended both time series, and it looks like, well, actually, a lot of the variability that we see in this lower North Atlantic deepwater layer corresponds to wind forcing in the surface. And what we know about wind forcing in the North Atlantic is that the NAO, just a spatial climate pattern of sea level pressure, actually controls a lot of the wind variability. So if we just take the NAO monthly time series against a normalized time series of Ekman transport and we plot those on top of each other, they agree pretty well as well. So we have these three things here. The MOC looks a lot like the lower North Atlantic deepwater, but I haven't detrended. Ekman and lower North Atlantic deepwater look a lot like each other, but I have detrended, and Ekman at 26 north looks a lot like the NAO, a basin-wide climate pattern for the North Atlantic. So what's going on? What's causing the variability? What's left over that we don't know about? So if we want to just look at the winds, this is what the winds typically look like in the North Atlantic, zonal winds. So you have, I always mix this up, westerlies coming from the west, blowing this direction, that's why I put the arrows on there, in the mid-latitudes, and in the opposite direction in the subtropical, tropical latitudes. And so this generates at 26 north, typically northward transport of surface waters. So typically, we have about 3 spheres northward of Ekman transport, and because of this assumption that what goes north must come south, that has to get distributed somewhere southward in the array. So if you just assume a barotropic response to the winds, which previous studies, analytical studies, numerical studies have suggested is reasonable, then in the top 100 meters you have this northward transport that's quite large, and distributed over the sort of 5,000 meters beneath, you have southward flowing water that compensates. And so this would seem like a pretty straightforward explanation for this relationship that we see between Ekman transport and lower North Atlantic deepwater transport, at least at first glance. There are a couple problems with it, though, one of them being that these have not been scaled in any way. So when you have an Ekman transport anomaly of 8 sphere drops, you have a lower North Atlantic deepwater transport anomaly of the same magnitude. And I realized I didn't put the colors on here. Purple is lower North Atlantic deepwater, and Ekman is green. Oh, the colors are sort of down there. And then if you want to see what this looks like in rather than in sort of a time varying sense, this is the basin average winds. So we have this pattern of westerlies over easterlies. This is the average of that, but now plotted in time. So what we can see is these particular events here, where the Ekman transport reversed strongly, what happened to the pattern of winds. So what you actually see is this typical pattern of, I'm going to do it again, westerlies has actually shifted, or it appears to have shifted southward. So suddenly your westerlies are over the array at 26 north instead of easterlies, which has reversed to the direction of the Ekman transport. And what that means is that if we have this same idea of the compensating flow, the 2009-10 winter, we had strongly negative winds, a strongly negative Ekman transport, and so then you would have the opposite sign effect in your deep transports. So it's sort of a simple explanation of what's going on. This seems to kind of work. So, right, so just to summarize that bit, much of the variability seems to originate in the compensation term, although we have evidence that I'm not going to go into here to suggest that it's appropriately applied. And on subannual timescales, we also have evidence that bottom pressure records, so pressure is another measure of transport. If you have pressure differences across a basin, it should drive transport, show much of the same observed variability in the lower North Atlantic deepwater flow. However, bottom pressure records can't measure on interannual timescales. So due to intrinsic drift in the way that bottom pressure is being measured in the ocean, you always have to remove sort of an exponential or a linear drift from your time series before you plot up your pressure records. And what that ends up with is a record of a transport estimate that can only recover subannual timescales. So you can't look at longer timescales that may be the ones that we're interested in. So going back to this plot between the MOC and lower North Atlantic deepwater transports, we see that they're co-varying on short time scales, but also on long time scales. So if you sort of fit by eye a low-pass filter to this, you see that, well, the MOC was anomalously strong since this is reversed, and now it's anomalously weak. And how can we investigate these transport variations when most of the variability originates from the compensation, and our verification for the compensation comes from bottom pressure records that can't do longer time scales? So we need an alternate way to sort of estimate what the transport is in the deep ocean, independent from these observations. So the method to use is the GRACE satellite system. So GRACE is a pair of satellites that are following each other exactly in the same orbit, and the measurement that they're making, they're not actually looking at the Earth. The measurement that they're making is the distance between those two satellites. And so what happens is, as this leading satellite goes forward, and say it feels the mass of Greenland in front of it, and it gets accelerated by small variations or large variations in the mass of the Earth beneath it. And so what it will measure is that the distance between these two satellites has increased. And then as these two satellites continue in their orbit, this one will get to the position where it also feels the acceleration due to this increased mass that's beneath it, and it'll accelerate and catch up with the leading satellite. And so you get this measurement of distance across the, between these two satellites while it's in orbit, and then all those measurements over sort of a 30-day time scale are then inverted to say, what kind of mass distribution on the Earth would give me this distance between these two satellites? And what it turns out is that they can back out estimates of ocean bottom pressure or ocean mass. So the effect of, say, sea level being higher here or water being denser here, pulling on this first satellite, they can back that out from these distance measurements between the two satellites. And the nice thing about GRACE is that unlike a single bottom pressure sensor that goes into the ocean and then you bring it back up and then you need to detrend it before you can look at the variability, this is a single system that's been operating since 2003, and so you should have this sort of continuous estimate of bottom pressure. Okay, that's what you hope. And in the autumn, Felix Landerer wrote this nice paper saying, well, if we use GRACE bottom pressure at 26 north, we can estimate transport, again through geostrophy, but looking at the pressure differences between the east and the west. And we get those pressure differences out of the GRACE satellite system, and we have this time series, now a 10-year time series, saying what is the transport between the east and the west. So this is just a record of the pressure variations in the west, a record of the pressure variations in the east. The amplitude is a bit smaller, and then east minus west, which should look like the transport. And these are estimated for bottom pressure over the depth range 3,000 to 5,000 meters, which is the same as the lower layer transports that we talked about earlier. And they showed that it doesn't really matter if you include the Mid-Atlantic Ridge, because at least from what Grace observes, the bottom pressure fluctuations on the east and west flank of the ridge are similar, and they cancel out. And if you do that, so this is transport estimates from Grace in blue of the lower North Atlantic deep water, and in black from Rapid, and you see reasonable agreement, very promising agreement. And this is low frequency variations that we can't otherwise do from bottom pressure estimates. Yeah. Yeah.
So I didn't read the measure of pressure, but why is it that the measurement from Grace is representative of that specific layer in the ocean?
Oh, so yeah, so what they did is they went and they have, it's sort of got a 300-kilometer spatial grid to it. And they say, well, I've got a grid point here and a grid point here, and spatially, so over sort of east of the Bahamas, and they interpolate that value onto bottom bathymetry locations. So they say, here's my spatial value of pressure here, here's my spatial value of pressure here. I'm going to interpolate that onto this finer depth grid.
But it's really slow pressure.
It's definitely slope pressure, yeah, yeah. And so they get what looks like pretty reasonable agreement. So very exciting. An independent estimate of the interannual variability of the lower North Atlantic deepwater transport. There's a lot of words, but it's the lower North Atlantic deepwater that we think is responsible for MOC variability, or at least those correlate very strongly. And from the rapid observations, the estimate of transports from lower North Atlantic deepwater are really highly correlated with this compensation term that's calculated as a residual. So it's not directly observed. So this is an independent direct observation of, or transport estimate for this deep layer. Okay. And how does this compare to what we've seen? So I kind of just said that. The MOC and lower North Atlantic deepwater transports, they look very similar, and some of it comes out of the winds. And then there's one problem. And the problem is that the Grace estimates, the ocean bottom pressure signal is a fairly small component of what these see. They see all sorts of things like the wobble and flex of the solid earth, which is a fairly large signal. They see the hydrologic signal, which is a fairly large signal concentrated on the land. And then they have issues with glacial isostatic adjustment, or the rebound of these regions that were depressed. So crustal regions that were depressed during the last ice age that are slowly rebounding, that add a trend to bottom pressure. And so it can be difficult to separate out the trend in mass due to the crustal rebound and the trend in mass due to the mass of the ocean changing. So in order to make these comparisons, they detrended their data first. They detrended the Grace data and they detrended the lower North Atlantic deepwater layer. If you do that with your Ekman transport, so Ekman being winds, being this high frequency variable thing, if you detrend it and low pass filter it and then compare it to lower North Atlantic deepwater, what you actually see is that even though we're talking about long time scale variations, we're talking about low pass filtered sort of 1 year, maybe 8 month and longer time variations, they're actually originating from short timescale fluctuations. So it's partial success. So it recovers the deep transport variability. It's an independent estimate, but because it was detrended, the main thing that's governing the variability that's being measured is coming out of the winds. Okay, so I was really disappointed by this. I was really disappointed by this because Grace seemed like this magic bullet that was going to go and give us the deep transport variability, long time scales, no problems with drift. Right. So in an attempt to try and see what we can get out of it, it doesn't give us the low frequency variability, but it does give us a spatial pattern of the variability. So we can actually look at the ocean beyond 1 latitude, beyond 26 north. Now this is also from Felix's paper, and it's just a simple regression between lower North Atlantic deepwater transport and GRACE at each of these sort of 3 degree by 3 degree pixels. And if you make this correlation, what you see is it's highlighting sort of a region where we think the deep western boundary current is. So it's highlighting a region in the west and saying that the fluctuations that are controlling the transport are coming from the west, and they're not spatially only located at 26 north, but they're spread out over the North Atlantic. So what can we learn about the spatial pattern from these bottom pressure fluctuations? So a typical thing to do if you have a spatial temporal data set is to calculate EOFs. So this is the first EOF for the GRACE data. And the time series is shown here in blue, and the time series for Ekman transport is in green. And so the time series, if you look at that first, it seems like it captures at least these 2 big dips in the Ekman transport. It misses this one, but actually there was an outage in the GRACE data during this time period. So it's unclear whether it wasn't there or whether it just missed it because the satellite was turned off. But the spatial pattern shows roughly the same thing. You see high pressure in the west along the mid-Atlantic ridge when this time series is positive, and during these time periods when it dipped negative, so the amplitude is in blue, so we have this negative amplitude, so it means low pressure in bottom pressure on the west, and if you have relatively high pressure and anomalously low pressure here, then you have water going from high to low pressure and through geostrophy in the northern hemisphere turns it northward. So that's when you have anomalously weak southward transport in the deep layers. So it seems to be showing us that you have anomalously deep southward transport in the deep layers, not just at 26 north, but at other latitudes as well. So this is a large-scale phenomenon, which makes sense because the winds are also a large-scale phenomenon. So this is again the first EOF, but it's for winds now, and it's showing the same pattern that we had, or a similar pattern that we had before, except the centers of action have been shifted a little bit, and we see that this time series of the winds is also reversed, so when this is negative, the winds switch direction, and you have the opposite direction flow. And if you compare these two things, so the spatial pattern of bottom pressure, spatial pattern of winds, they agree pretty well. Except that they don't look anything like each other. So you have a bottom pressure response in the ocean that's actually spanning positive and negative signs in the EOF in winds, and it's sort of curling up the eastern seaboard and curling down the western flank of the mid-Atlantic ridge. So it has this curious spatial structure. So it's a bottom pressure response, which is a deep transport response to wind fluctuations that can be explained in about the same way that we've said before, where we have winds typically going to the west, generating a northward Ekman transport. This is from the Jane and Morotsky paper. And they say that then generates, if you have water anomalously fluxing to the north, that generates a high pressure here and a low pressure here. And then other things are set up. This eventually generates a geostrophic flow due to a pressure gradient between east and west. So they explain how you get from winds to a geostrophic flow in the opposite direction. But this doesn't necessarily explain the spatial pattern that we see here. So it's curling up the bathymetry, and it's the same sign response. If you were just going according to this, you would expect the same sign response roughly underneath the same sign wind anomaly, and the opposite sign response underneath the opposite sign wind anomaly. I'm going to skip that. It says some of the same things. I'm looking for a slide, but it's not here. Okay. Well, this is just to say they're correlated. So the EOF amplitudes from GRACE and from wind are correlated. You filter them a little bit, so similar to the Landover paper, and they're still correlated. And you filter them on longer time scales, and really they're still correlated. And this gray bar here is showing that as you apply each of these filters, how broad does the influence of these peaks get? So when it's monthly, the influence of the peaks is narrow. When you filter with 8 months, it gets broader. And when you filter with 1.5 years, these things are smoothed into what look like these large duration anomalies. But all you've done is filter high frequency variability. Okay, so This is the same thing. So this is the barotropic response, but you would expect an opposite sign response underneath the two different wind patterns. And this difference in the response between these two can be explained speculatively following some discussions with folks at Oxford, Helen Piller, Helen Johnson, and David Marshall, where they use an adjoint model to investigate the ocean response to wind and buoyancy fluxes. But what they see is that if you have this same sort of issue where you have your winds going to the west, you have northward Ekman transport, and then if you have a continental slope that's going in this direction, that water is going to pile up on the shallow slope, and it's going to get sort of concentrated with a high pressure region along the slope, which seems to be what's happening here. And then they say that actually that anomaly can spread very rapidly through barotropic adjustment following F/H contours. So it spreads very rapidly across this region. In this subpolar region, where you have the opposite sign effect, what you can actually have is winds from the west, southward Ekman transport that then's piling up not on the continental slope, but on the mid-Atlantic ridge. And so you can have water piling up along here so that you have a high pressure here. So even though you have an opposite sign wind, you can have the same sign pressure response because it's piling up against these different sloping bottom topography. Okay, and then one further example of where this spatial pattern has cropped up before in talking about the overturning circulation and its response to winds. This is from a paper by Steve Yeager, also last year, who looked at, in particular, the strong 2009-10 wind events and said, this is what the barotropic ocean response is to those wind events, and they see a spatial pattern that looks quite a lot, in some ways, like the pattern coming out from Grace. So direct observations of the ocean, and this is a numerical model simulation, but what they see is this strong response in the west, and then some suggestion that it's coming down the mid-Atlantic ridge well, not on the east, but down the middle of the basin. So what we've seen from Grace is that you can estimate transport fluctuations in the deep layer, that most of the variability that's observed in the deep layer and by Grace is due to a barotropic response to wind forcing, and that the spatial pattern of this barotropic response is associated with these high pressure anomalies following bathymetry in the west and also high pressure anomalies following the mid-Atlantic ridge in the middle. Skip that. Okay, so winds drive deep transport fluctuations. This was Ekman and lower North Atlantic deep water. The spatial pattern of the pressure anomalies is set up by just a simple barotropic response, but influenced by topography. And Steve Yeager goes on to say that it actually creates a depth-dependent structure anomaly in the overturning, so that you have an anomalously strong overturning below 2,000 meters, so that most of that transport anomaly ends up in the lower layer, 3,000 to 5,000 meters, rather than depth-independent below 1,000 meters. And that this pattern gets set up by the wind anomalies and then is spread quickly along bathymetry through some sort of fast barotropic wave adjustment. Okay, that's my conclusion.